we're used to seeing things from a particular point of view. That is, from a particular frame of reference. And things look different to us under different circumstances. At the moment, things look
You look peculiar. You're upside down.
No, you're the one that's upside down.
No, you're upside down.
No, I'm not. He's the one that's upside down, isn't he?
Well, let's toss for it.
All right.
Okay. You lose. He's the one that's really upside down. You better come into my frame of reference now.
All right. My frame of reference was inverted from what it usually is. That view of things would be normal for me if I normally walked on my hands.
This represents a frame of reference. Just 3 rods stuck together so that each is at right angles to the other 2. Now I'm going to move in this direction. You see the frame at the same spot on your screen, but you know I'm moving this way because you see the wall moving this way behind me. But how do you know that I'm not standing still and the wall moving? It was the wall that was moving. Now the wall has disappeared, and you have no way of telling whether I am moving or not. But now you know that I'm moving. The point of this is that all motion is relative. In both cases, I was moving relative to the wall, and the wall was moving relative to me.
All motion is relative, but we tend to think of one thing as being fixed and the other thing as being moving. We usually think of the earth as fixed, and walls are usually fixed to the earth, so perhaps you were surprised the first time when it was the wall that was moving and not Dr. Hume. A frame of reference fixed to the earth is the most common frame of reference in which to observe the motion of other things.
This is the frame of reference that you're used to. The frame is fastened to the table. The table is bolted to the floor is anchored in the building, and the building is firmly attached to the earth. Of course, the reason for having 3 rods is the position of any object, such as this ball, can be specified using these 3 reference lines. This reference line points in the direction which we call up, which is a different direction here than it is on the other side of the earth. And these 2 reference lines specify a plane, which we call horizontal or level. In this film, we're going to look at the motion of objects in this earth frame of reference and in other frames of reference moving in different ways relative to the earth frame. Well, let's look at a motion. This steel ball can be held up by the electromagnet. Now I'm going to open the switch, and you watch the motion of the ball. The ball is accelerated straight down by gravity along a line parallel to this vertical reference line.
As you can see, the electromagnet is mounted on a cart that can move. And I'm going to do exactly the same experiment that Dr. Hume did, but this time while the cart is moving at a constant velocity. The cart is pulled along by a string which is wound around this phonograph turntable, and that pulls it with a constant velocity. When the cart passes this line, the ball is released, as you can see. I'm going to start the cart down at the end of the table so that by the time it gets to this point, I can be sure it's moving with a constant velocity. Now, I want you to watch right here so that you will see the ball falling. I think you can see that the ball landed in exactly the same position that it did before. when Dr. Hume did the experiment with the cart fixed. But this time, the ball could not have fallen straight down. Let me show you why. The ball was released at that point. If it had fallen straight down, because the cart moves on in the time that it takes to fall, it would have landed back here somewhere. But it didn't. Now I'm going to do the experiment again. And this time, I'm going to let you watch the motion through a slow motion camera, which is fixed here. As the cart moves by, the ball will fall, and you can watch in the slow motion camera. I'll show you this again. This time there'll be a line on the film so that you can see the path. I think that you can see that the path of the ball is a parabola. But all of this has been in a frame of reference fixed to the earth. How would this motion look in a frame of reference which was moving along with the cart? Frame of reference like that. Well, so that you can see what it looks like, I'm going to fix this slow motion camera so that it moves with the cart. Like this. I'm going to do the experiment again. And incidentally, I'll start it, and then I'm going to stand here so that when the ball falls, you will have something which is fixed as a reference point. In the moving frame of reference, I think you could see that the path of the ball is a vertical straight line. It looks exactly the same as it did before when Dr. Hume did the experiment with the cart fixed. If we were moving along in this frame of reference and we couldn't see the surroundings, then we wouldn't be able to tell by this experiment that we were moving at a constant velocity. As a matter of fact, we wouldn't be able to tell by any experiment that we were moving at a constant velocity. I'm going to do the experiment once more. And this time, I'm not going to stand here behind the ball as it falls so that you won't have any fixed reference frame. As far as you're concerned, that time, the cart wasn't necessarily moving at all. That time, when you couldn't see the background, then I think perhaps it was harder for you to realize that you were in a moving frame of reference. The important thing to realize here is that all frames of reference moving at constant velocity with respect to one another are equivalent.
Dr. Ivy showed you what the motion of the ball that was released from the moving cart looked like in the earth frame of reference and in the cart frame. The motion looked simpler from the cart. Now I want you to watch the motion of this white spot. You probably see the spot moving in a circle. But this is what its path is actually like in the earth frame of reference. This is your normal frame of reference. You saw the spot moving in the circle because your eye moved along with the cart. You put yourself in the frame of reference of the moving cart. So you see, it isn't always true that we view motion from the earth frame of reference. When the motion is simpler from the moving frame, you automatically put yourself in that moving frame.
Now we're going to do another experiment on relative motion to show how to compare the velocity of an object in one frame of reference to its velocity in another frame of reference. If I give this dry ice puck a certain start, it moves straight across the table with a speed which is essentially constant because the forces of friction have been made very small. This is just the law of inertia. An object moves with a constant velocity unless an unbalanced force acts on it. Now, will you give it the same start backwards?
I'll try.
Dr. Hume gives it the same start, it moves back in this direction with the same velocity. Now we are on a car here, a car which can move and which really is going to move in this direction, and we're going to repeat the experiment. All right, let's go. If we were making measurements here, then we would observe the same velocities, that is, the same experimental results that we did before. And so would you, because you are observing this experiment through a camera which is fastened to this cart. That is, you are in the moving frame of reference with us. But now we're going to do the experiment again, and this time you watch through a camera which is fixed in the Earth frame of reference. Now concentrate on watching the puck. Don't let your eye follow us. And I think you'll see that it'll move faster that way and not so fast this way, relative to you and relative to the wall behind. Here's the cart, which was moving along in this direction with a velocity u. We were sitting on the cart at a table. Here I am over on this side, and Dr. Hume was on this side, and we were pushing this puck back and forth on the table. When I pushed it, it went in this direction with a velocity v, and when Dr. Hume pushed it, it went in this direction with the same velocity v, but this is the velocity relative to the cart. What about the velocity relative to an observer on the ground in the fixed frame? Well, if it was pushed in this direction, its velocity is u plus v. If it's in this direction, its velocity is u minus v. This is all very reasonable. There's nothing very hard to understand here. The surprising thing about this expression is that it is not accurate in all circumstances. At very high speeds, and by high speeds I mean speeds close to the velocity of light, this expression breaks down. At these very high speeds, we have to use the ideas about relative motion developed by Albert Einstein in his special theory of relativity. However, for all the speeds that we are ever likely to run into, this expression, u plus or minus v, is completely adequate.
So far, we've been talking about frames of reference moving at a constant velocity relative to one another. Now I'm going to do the experiment with the dropping ball again, only this time the cart will be accelerated relative to the Earth frame. These weights will fall and give the cart a constant acceleration. I'll put the ball up, and then I will release it. The motion is very fast, and I want you to watch at the point where the ball is released from the fixed camera. Ready? I don't know whether you saw that or not, but the path of the ball was the same as it was before, only this time it landed in a different spot. This is because the car kept on accelerating in this direction as the ball was falling. Now I'm going to let you see it again with the slow motion camera fixed onto the cart. This time you saw the ball moving off to one side and not following down the vertical reference line as it did in the constant velocity case. Now suppose you were in this accelerated frame of reference. How could you explain this motion? Gravity is the only force acting on this ball, so it should fall straight down. But if the law of inertia is to hold, there must be a force pushing sideways on the ball in this direction to cause it to deviate from the vertical path. But what kind of a force is it? It isn't a gravitational or an electric or a nuclear force. In fact, it isn't a force at all as we know one. So we're left to conclude that since there is no force that could be pushing in this direction on the ball, that the law of inertia just does not hold. This is a strange frame of reference. We call a frame of reference in which the law of inertia holds an inertial frame. The law of inertia holds in the Earth frame of reference, so it is an inertial frame. The cart moving at constant velocity relative to the Earth is an inertial frame. But the cart which is accelerated is not an inertial frame. Because the frame of reference that we're used to living in is one in which the law of inertia holds, when we go into a non-inertial frame, like the frame of the accelerated cart, our belief in the law of inertia is so strong that when we see an acceleration of the ball sideways, we think there is a force causing it. So we make up a fiction that there is a force. And sometimes we call this a fictitious force. Fictitious forces arise in accelerated frames of reference. The frame is accelerated in this direction, so you in the frame see an acceleration of the ball in this direction, and you say that there is a force causing it.
What's happening this time? Why doesn't the puck move straight across the table as it did before? As you can see, it doesn't. So, if we believe in the law of inertia, then we must believe that there is an unbalanced force to change the velocity of the puck. But this puck is nearly frictionless, so what can be exerting this unbalanced force on it? Suppose that you watch the motion, this time, through a camera which is fixed in the Earth's frame of reference. I think if you concentrate on watching just the puck, you can see that it is moving in a straight line, and that therefore there is no unbalanced force acting on it. Now we're going to stop this rotation so that I can talk to you about what is happening here. I don't know about you, but I'm dizzy. In the Earth fixed frame of reference, there was no unbalanced force, but in the frame of reference rotating in this turntable, there was an unbalanced force because the velocity of this puck kept changing. This was a fictitious force. The rotating frame is a non-inertial or accelerated frame, just as the accelerated frame of the cart that Dr. Hume showed you was. You know that every object which is moving in a circle has an acceleration towards the center of the circle. This is the acceleration that has a special name, the centripetal acceleration. Now you hold this puck for a while, hold it steady, while the turntable is rotating. Now I'll get off. Are you ready? I'm ready. Start the rotation. You can see that now the puck is moving in a circle. Dr. Hume is exerting a force to keep it moving in the circle, and you can see this from the fact that the rubber ring is extended. He is exerting the centripetal force, and this is the only horizontal force acting on the puck. But now let's look at it again from his point of view in the rotating system. He is exerting a force towards the center of the table, and yet the puck is standing still, or at least more or less still. There is some vibration. Now, he believes in the law of inertia, so he thinks there's an equal force on the puck away from the center of the table, so that there is no unbalanced force. This outward force on the puck is the fictitious force in this case. Sometimes it's called the centrifugal force. In the fixed reference frame, there is no outward force on the puck. Now, suppose that Dr. Hume stops exerting a force. Watch the puck. In the fixed frame of reference, the puck moves off in a straight line. There is now no unbalanced force acting on it. Now let's look at it again from his point of view in the rotating system. When he releases the puck, which to him was at rest, it moved. The force away from the center is now an unbalanced force on the puck, to him. Remember, to us, the outward force on the puck is fictitious, because in our Earth frame of reference, it doesn't exist. But to Dr. Hume, in the accelerated frame of reference, it's a perfectly real force.
I hope by now Dr. Ivy and I have convinced you that a rotating frame of reference is not an inertial frame. Now, you've all been told that the Earth is rotating about its axis, and that also it travels in a nearly circular orbit around the Sun. Why then do we find that in a frame of reference attached securely to the Earth that the law of inertia seems to hold? Why don't we observe fictitious forces? The size of the fictitious forces which we have to introduce in a non-inertial frame depends on the acceleration of the frame. The smaller the acceleration is, the smaller the fictitious forces that we introduce. Now, here is a frame of reference attached to the equator of the Earth. The acceleration of this frame is really very small. Because the Earth is spinning about its axis, it has an acceleration directly inward of 3/100ths of a meter per second squared. So on a 1 kilogram mass at the equator, there is a fictitious force acting directly upwards of 3/100ths of a newton. But this is masked by gravity, which is a force downward of 9.8 newtons. So the net downward force is smaller than that of gravity alone. So if I dropped a mass of 1 kilogram at the equator, the acceleration would be slightly smaller than that due to gravity alone, but not really very much. Now, the acceleration of the Earth in its orbit is even smaller still and produces even smaller effects in our frame of reference. Now, I said that the Earth was rotating about its axis. How do we know that this is so? Well, if you take a time exposure photograph of the stars, they seem to be moving in circles about the pole star. But all motion is relative. Is there any way of telling which is moving, the Earth or the stars? The fact that it is the Earth which is rotating can be demonstrated by means of a pendulum. If I set a pendulum swinging, it swings back and forth in a plane. Now, it turns out if this pendulum were at the North Pole of the Earth, the plane of swing would remain fixed relative to the stars, but would rotate relative to the Earth. Now, I'll have to show you what I mean. This pendulum is at the center of this turntable, which will represent the Earth. Now, I'm going to start the table turning around in this direction. I'll put a black arrow on so that you'll remember. All right, start the rotation. The pendulum is at the North Pole of the Earth, and you are in motion as you ordinarily do, standing on the Earth. The plane of swing rotates in the opposite direction from the rotation of the turntable and at exactly the same rate. Now look at it from the fixed camera, which will represent the frame of the stars. The turntable the Earth rotates, but the plane of the pendulum remains fixed. A pendulum used for this purpose is called a Foucault pendulum. You saw me start one at the beginning of this film. Let's look back again now. This Foucault pendulum drops sand as it swings. I think you can see the faint line where the sand trail began. The amplitude of swing is decreasing. The sand trail isn't as long now. But the important thing to see is that the plane of swing has been rotating during the half hour that we've been talking to you.
An inertial frame of reference is one in which the law of inertia is valid. All frames of reference moving at a constant velocity with respect to an inertial frame are also inertial frames. We use the Earth as an inertial frame of reference, but it is only approximately one. It has a small acceleration with respect to the stars, for example. The frame of reference of the stars is the best we can do when we look for a frame of reference which is, for all practical purposes, fixed.
An accelerated frame of reference is not an inertial frame. And when we are in an accelerated frame, we have to introduce forces, which we call fictitious forces, in order that the law of inertia and the other laws of physics don't change.